equations and chemical equations. And so what we want to do is we want to be able to run calculations on those equations, because chemists are able to say, if I run this equation, this reaction, starting with this quantity of this reactant, I am able to produce this quantity of this product. Or they can say, I need this amount of the product. How much do I need to start with in the reactant? Or they can even go further and they can say, this reaction is 80% efficient. I need to produce X amount of the product. How much do I need to start with? We'll be able to do that too. Or they can say, how efficient is this reaction? Because I need to know if it's worth it, the cost, to run this reaction at all. All of these are valuable pieces of information. And so these are the information that by the end of the next 2 chapters we will be talking about and we'll be running and calculating. All right, but we need to start at a very simple level. And the simple level we're going to start with is, today we're going to start by running molar mass. So a scientist named Avogadro came up with something called Avogadro's number. And you've seen it before. It's 6.02 times 10 to the 23rd particles. And that could be atoms or ions or molecules or whatever. Bicycles, marshmallows, chocolate chip cookies, all 3 of which would throw the Earth off its axis. But this number is so large that if we had this many fireballs, you know, those individually wrapped fireballs that are smaller than a golf ball, like they're about the size of a die, you know, a dice, you know what I mean? About the size of a dice, a little bit bigger, they would more than cover the Earth, including oceans. That's how large this number is, those fireballs, okay? So Avogadro said there are this many particles in 1 mole. And so there's where that word mole comes from, that word mole, which you guys made the mole because this was so important. And so this many atoms in a mole, this many ions in a mole, this many molecules in a mole. The word mole is like the word dozen. It represents a number, like 12, right? A dozen means 12. If I say I have a dozen donuts, you know I have 12 donuts. If I say I have a dozen bicycles, you know I have 12 bicycles. If I say I have 1 mole of carbon atoms, now you know I have this many carbon atoms. This number is how many is in a mole. I would never say I have 12 dozen is equal to 1 bicycle, right? 12 dozen equals 1 bicycle. No, that's just wrong, because that's saying 12 times 12 is equal to 1, right? Because a dozen means 12. So that's saying 12 times 12 is equal to 1. That's wrong, right? 12 bicycles equals 1 dozen, which equals 12, right? So 12 and then 12. Does that make sense? So I would never say 6.02 times 10 to the 23rd moles is equal to 1 particle. No, I would never do that, because this number right here equals this word equals this number. All right? So I would never put this number with this word, just like you wouldn't put 12 with a dozen and then say that's equal to 1 egg. No, 12 eggs is equal to 1 dozen, all right? This is one of the most common mistakes that kids make, is that they put this number with moles. It already happened twice this morning. Like 2 kids kept putting them in the wrong place, all right? So it happens all the time. All right, so what we're going to work on today is molar mass. This is the mass in grams of 1 mole of a substance. Now, that substance could be elements, molecules, could be anything, right? So if it's an element, then it's going to be 6.02 times 10 to the 23rd atoms of that element, right? Because it's an element, so it comes in atoms. If it's a compound, then it's going to be 6.02 times 10 to the 23rd molecules of that compound. All right? So whatever it is, it's still going to be 6.02 times 10 to the 23rd of that, whatever it is. And then what we want to know is what's the mass of 1 mole of those. Now, if you look on the periodic table, you see one, for example, you see 12.01 AMUs for 1 atom of carbon. For molar mass, you take that same number, you just change it to grams for 1 mole. That's why Avogadro's number is so important, because it's 12.01 grams for 1 mole of carbon. So it's exactly the same number, just the unit is changed. That's why Avogadro's number is so important, because it allowed us to go between grams and atoms, molecules and atoms. So it made chemistry at the molecular level just by doing calculation. So in other words, carbon is 12.01 grams per 1 mole, right? 1 mole. Or, remember at the beginning of the year, we were setting up conversions. 12.01 grams of carbon is equal to 1 mole of carbon. And there's your conversion. And what we would do is we would take that conversion and we would say that is the top and the bottom of one of those boxes in a conversion. And we're going to be doing more conversions today. All right, we're going to be converting like from moles to grams, and from moles to molecules, and moles to atoms, and then from atoms to grams. Okay? All right, so that's easy. Doing atoms, super easy. So magnesium, number 12, 24.31 grams for 1 mole of magnesium. Hydrogen, 1.01 grams for 1 mole of hydrogen. Super easy. But what about compounds? Well, so let's say I'm going to do water. So what I'm going to do is I'm going to say 2 hydrogens. So I say 2 times 1.01, which is the mass of water, of hydrogen, right? So that's 2.02. And then 1 oxygen, so 1 times 16.00. So 16.00, and that gives us 18.02. And so water has a molar mass of 18.02, notice the units, grams per mole, which is grams per 1 mole. 1 mole of water equals 18.02 grams of water. All right, there's my conversion factor that I can use. All right, let's do a little one that's a little bit more complicated, okay? So now let's do ammonium carbonate. NH4, 2, CO3. So I'm going to do the same thing. I'm going to break out my, my elements, all right? Exactly like I did before. So I'm going to start with 2 nitrogens, 8 hydrogens, 1 carbon, and 3 oxygens. So that's what I find in that compound. So 2 times, I look up the nitrogen mass on my periodic table. 14.01, so that gives me 28.02. 8 times, I look up hydrogen on my periodic table. 1.01 is 8.08. 1 times carbon, which is 12.01, so I get 12.01. And 3 times 16, which is 48. I add these all up and I get 96.11. So that's 1 mole of NH4, 2 CO3 is equal to 96.11 grams. Okay, so now, this is 96.11 grams per mole. So now I've set up my conversion factor. All right, any questions so far? All right, now the next thing that we want to do is we actually want to make a conversion here. All right, so let's say I had 4.7 moles of ammonium carbonate. And I want to convert that to grams. So as we know, when we have a situation like this, the unit that goes down is the one that's up. So moles are going to go down because I want to go to gram. How many moles? 1 mole. Because my conversion factor here is 1 mole is equal to 96.11 grams. Now, we had a situation earlier where kids were kind of confused. They said, oh, 96.11 moles, right? So I asked you, when you step on a scale, is it like 128 U's to 1 pound? No, it's 1 U and 128 pounds, right? So that's the same way here. It's 1 mole and it's many grams, right? Because this mole, which is oh so many particles, right? Look up here. Oh so many particles is in 1 mole, right? So this 1 mole is going to step on the scale. You're going to put it on the scale. And it's going to weigh 96.11 grams. It's going to weigh many grams. So when I ask you, like, how many moles is going to go down here, because you're looking at moles to grams, it's many grams to 1 mole. Just like it's many pounds to 1 U. Does that make sense? It's not going to be many moles to 1 gram. It's not many U's to 1 pound. Grams is something that there's many of. When you're comparing grams and moles or pounds and U, there's many grams, many pounds, 1 U, 1 mole. That's what I'm massing, is the mole, right? So 1 mole has a mass of 96.11 grams. Now I can cancel that out, the moles. And that's the whole point of putting them on top and bottom, is that I can cancel that unit. And when I do that, I'm left with grams of NH4, 2 carbonate, right? Ammonium carbonate. So when I multiply this out, I get 2 digits in my answer. So I get 4.5 times 10 to the 2 grams of ammonium carbonate. So now I know how much my 4.7 moles of ammonium carbonate weighs. Now, always the next question from students is, but Ms. Paxton, I could have done that without the boxes. And my answer is, we have 3 chapters of this. I know what's coming and you don't, okay? So bear with me, because I know what's coming and you need to understand how the boxes work, okay? Next. What if I wanted to go from grams to moles? So let's say I had 16.9 grams of CO2, something really easy, and I want to know how many moles that is. So the first thing I would need to do is to get a conversion unit that I can use to go from grams of CO2 to moles of CO2, and that would be grams per mole, which is the molar mass of CO2. So I'm going to take CO2, and I'm going to do 1 carbon, and I'm going to take 2 oxygens, that gives me a total of 44.01 grams per mole. So again, 44.01 grams of CO2 is equal to 1 mole of CO2. So again, I put the 1 mole of CO2 on the scale and I get 44.0 grams. So 16.9 grams of CO2. That's what I'm going to start with. What unit goes down? Grams of CO2. How many? 44.01. 1 mole, 44.01. Even if you're looking at this, it's 44.01 grams over 1 mole. Okay? So 44.01 grams of CO2, 1 mole. The number has to stay with the unit. All right? I can have 1 truck and 4 tires, but I can't have 1 tire and 4 trucks. I can have 1 truck and 4 tires, or I can have 4 tires and 1 truck. So I can flip them around as much as I want, but the number has to stay with the unit, because I can't have 1 tire and 4 trucks. Okay? Now I take this and I divide it by this, and I have 3 digits in my answer, so I get 3.84 times 10 to the minus 1 moles of CO2. Now this is a little confusing because I don't understand, what does this mean, 3.84 times 10 to the minus 1 moles of CO2? What is that? But let's try and remember. A mole is a number, okay? So a mole is 6.02 times 10 to the 23rd particles. So this is almost 0.4 times this number. Because remember, this is like a dozen. So this is like 0.4 times a dozen kind of thing, right? So this is 0.4 times this number of particles. But we don't need the number of particles. I just want you to know it's like 0.4 times a dozen kind of thing, right? We don't need if I tell you if I have 0.4 of a dozen, I don't need to tell you that I have 0.4 times 12. I'm just telling you I have 0.4 times a dozen. Oh, okay, that tells me, right? Okay, so I'm telling you 0.4 times this number. That's what's in this number moles. So it actually is a number. It's not a thing. It's a number. All right? Okay, so to recap here, Avogadro's number is this many particles, and it's equal to 1 mole. That's what we call it, a mole, just like 12 is called a dozen, okay? If you're doing an element, you're looking at atoms. If you're doing, unless of course it's a diatomic element, in which case it's molecules, right? If you're doing a compound, you're looking at molecules. To find the molar mass of an element, you look on a periodic table. To find the molar mass of a compound or a molecule, then you're going to add them up. When you convert, you set up your conversion factor, which is going to be so many grams is equal to 1 mole. So many grams is equal to 1 mole. Because this fraction here is like this, 96.11 gram over 1 mole. That's what this fraction is, grams per 1 mole, all right? So I can flip this around any way I want so long as the numbers and the units stay together, okay? And then that means I can go from grams to moles, or I can go from moles to grams. Questions? Okay, let's go to the boards.